Okay. Good afternoon, everyone. Thank you for being here and even online. So today we are going to organize the nano session, NANO1, which is nanometals and its application in photocatalysis. And the time is 3:30 to 5:30. I am also Carry, so I'm going to host this session. So first, because of the yesterday's, actually we had two or three presentations at the same time. So it is very what we say difficult for the presenters and also for us now. It is very much uh, so without timing. So I will going to start for presentation with Dr. Rodriguez Vallejo with the CCID 153 photocatalytic hydrogen production and CO2 reduction using zinc oxide, graphene oxide composites, a sustainable microwave assisted synthesis via orange relays. Please, Dr. Rodriguez, can start your presentation.
Thank you. Well, I'm going to talk about zinc oxide synthesis process that I performed by using otra vez, no se ve la pantalla.
Sí. Un momento.
Well, the idea of this work is to synthesize this zinc oxide. At the beginning, I was only looking for what happened with the compound, with the particles. I used microwave radiation. In previous works, I have used this technique for another semiconductor materials. We have obtained very well defined morphologies. So in this case, I was looking for what happened to the zinc oxide and what kind of morphology we should obtain. But I didn't expect, to be honest, the appearance of the graphene oxide. So this was very interesting. This work, I published part of this work previously, but for the catalysis of dyes. So this is a small part of it that was mixed into English. And it's also interesting. Well, this is the content of the presentation. I'm going to talk about the synthesis process, green chemistry, the methodology, and the results, and some conclusions. Well, all we know about the environmental problems, that we have not only in Mexico but globally now. So this is related with the emission by using fossil fuels mainly. So we have to do something. There are a lot of technologies used or that follow this tendency to abort this issue. In my case, I work with photocatalysts for wastewater treatment, but also I am interested in production of solar fuels like hydrogen and some others related with the photoreduction of carbon dioxide. For example, methanol, acid formic. So by this process is very simple, in which we use semiconductors that absorb light, and this photogenerates holes and electrons. So this moving to the surface of the compound, and once they reach the surface, they enter in contact with different species, for example, water, a pollutant. For this case, in the case of the production of hydrogen, it reaches the surface and enter in contact with, for example, with protons. So the electrons move to the proton of hydrogen, and it becomes into hydrogen fuel. In the other band, the holes react with water, and in this case, form oxygen and another species that go to the conduction band and again react with the electrons. In the case of photoreduction of carbon dioxide, it's more or less the same process. But I expect that with these pictures, you have at least the idea of photocatalysis or photocatalytic process. Well, microwave synthesis is a very simple and fast synthesis method. In a previous work around 2016, I was working with Kesserite, copper, zinc, tin, and sulfide or selenite. In that moment, this material was the perovskite of our times. It was the most heat topic. And it was used for solar cells mainly to develop absorbers, like now perovskite is. In that moment, this material, this Kesserite, was synthesized around for very long times, maybe 24 hours, in some cases 72 hours. This means three days. So in that moment, when I started to work with this material, I used a microwave synthesis, and I achieved this same compound, but only one hour, or even 15 minutes also. So the process was very short. This technology also allows to have a very good control in the reproducibility of the material and a higher yields and pure product. So it's a very good technology to develop semiconductor, mainly because another aspect is that, for example, in a conventional synthesis, for example, in a hot plate or in an autoclave, we have to heat the plate by conduction. The conduction and the heat by the conduction reaches the baker, for example, and the bakers, once it's heat, it hits the liquid. So we have convection process by heating the system. In this case, we have radiation, which goes directly to the liquid. If the liquid has something special that to respond to this microwave radiation, it tends to move. It rotates, or they move that way and in the reverse, because we have an electric field that is moving. So this promotes friction and heats the solution. So we have in this specific place a superheating effect. So we can reach states that or conditions that we cannot reach by a single synthesis in autoclave or in a hot plate. So this is another reason that this is a very good technology. So now, why do I use zinc oxide? Zinc oxide is a very well-known material. It presents a band gap around 2.3 to 2.2. It works with UV light, so we lost a lot of part of the light of the visible light. It has a very good electron mobility. However, it has a very good cold mobility, so it is a very good oxidant, but not reductant. It is friendly environmentally. Actually, we use it, for example, for the feed, because it has anti-fungal activity. Also, for example, in the green, to protect from the sunlight, in the protector solaris, for example. So it has a lot of properties that make it a very good good candidate to work with feed. Another relevant aspect is that it has suitable band position. So, for example, the potentials are between the band gap. So we can develop different reactions. In this case, I work with orange peel. Why orange peel? Because we have orange around the world. So this material is, or this waste is well focused on different industries. For example, with candies, sodas. A lot of places has this well focused material or waste. It has a lot of phytochemicals. So, for example, organic acid, flavonoid, essential oil, pectin, tannins. The idea is to produce the zinc oxide, but without the need to use conventional auxiliary agents. For example, SBS, urea, or another one. No, we only use water, ethylene glycol, and that is to promote the extraction of these phytochemicals and the zinc source. No, in this case, zinc acetate. This is the process. The process is very simple. Once we have the orange peel, we dry it in a conventional oven and put it in the sun. Then we blend it to obtain the powder. Finally, we take part of the powder and we heat it in the presence of ethylene glycol and water to extract, by heating, extracting the phytochemical compounds. Then we remove the organic material and we took 60 milliliters of this extract and we add some part of around 12 grams of zinc acetate. We integrate and we introduce in the microreactor only for 10 minutes and this temperature. As you can see, the time is very fast. Actually, the process is previously by the total process of heating lasts 15 minutes because the previous 5 minutes is a ramp of heating from the ambient condition to this temperature. And at the end, the cooling time is around 30 minutes. So in less than 1 hour, we have the material. Once that we have the material, we wash it with water and ethanol by a conventional process by centrifugation. And then the powder is dried in a conventional oven around 105 Celsius degrees. Overnight is sufficiently. And at the end, we anneal this material. In a previous work, we test 3 temperatures, 450, 600, and 750. This was the best temperature for that process. That was photocatalysis of dyes. But we observed that photoluminescence was better, or was the signal of the photoluminescence was smaller. So we have better transport electrical properties. So at the end, this was the best condition. So that's what I only use in this work, this temperature. These are the results. In the bottom, we have the powder obtained directly from the microwave reactor without the annealing process. As you can see, we obtained directly the material, the zinc oxide. This is very simple to understand because ethylene glycol has some OH species that bond with the zinc, forming zinc hydroxide. So when we heat the solution, it immediately precipitates as a zinc oxide. However, we cannot use this material because it has a lot of organic content. It tends to float in the solution, so we cannot integrate it. So we cannot use it as a photocatalysis for dyes or photocatalysis for producing hydrogen or photoreduction of CO2. So we have to anneal. The condition was this, and as you can see, the only thing that is moving only by XRD that we can detect is that we increase the crystallinity of the material. We estimate the band gap by Wellman function once we have the diffusion reflectance. And as you can see, the band gap is around 3.16, which is smaller than the conventional reported. This was the first time that I suspected it was something different. Actually, the zinc oxide powder directly from the microreactor it was brown, so it had a lot of organic content. Once we annealed, the powder was gray. That's the reason that the band gap is smaller. We performed Raman spectroscopy, and in this moment we observed that we have some organic material in the compound. We observed the traditional vibrations of zinc oxide associated with the bonding between oxygen and zinc. But also we observed the D and G signals related to the presence of carbonous or graphene materials. For example, graphene oxide or reduced graphene oxide. We proved this by FITR. infrared spectroscopy, and by XPS, I only present XPS, and by a decomposition process, we observe the different functional groups that are in the sample. This is very important because it helps us to absorb contaminants in the case of photocatalysis or dyes, but also it helps us to increase or to enhance the conductivity of the material. It works as the graphene oxide is reported to work as a trapping electron, so it reduces the recombination process. This is the morphology of the material. As I said before, microbial synthesis gives us a very good, well-defined morphology. We obtain some spheric hollow spheres. Sorry. Actually, if we reduce the amount of zinc oxide, we obtain a very good or another kind of morphology. It is some a double and a sphere in the interior and outer hollow sphere. Once we hit the material, it explodes. It is good for us because we increase the surface area. We perform some electrochemical experiments. As you can see, this is the space of what Shockley plot. With this, we find the kind of conductivity of the material. We have a positive slope, which gives us that, or it means that we have an N-type material. It means that it is a photoanode, which means that we can promote oxidation reactions. Here is the band diagram associated with that result. This result, this flat band potential is the conduction band. Is this one. If we add the band gap, we obtain the valence band. So all the reaction in theory that falls inside of the gap. This is the gap. Sorry, this is the conduction in the valence band. So all the reactions that falls inside of the gap, it is possible to perform or to achieve this condition. Only if we have the right reaction. For example, in this case, we are promoting oxidation process. So the only one reaction that is developed under this condition is this one, because these two are the complementary reactions. These are reduction process. So the material works very well with this. So at the end, we're going to have, or we're to obtain hydrogen and acid forming in the work process, but we have a very poor performance for the other two reactions because we don't have something to perform this. This will be developed or increased by using another co-catalyst, or for example, another semiconductor, for example, a P-type material. A P-type material is a material that promotes reduction process because it has the positive behavior. This was the condition for producing hydrogen and formic acid. There is two different experiments. These were performed in Monterrey. Well, this is at the end the production of the hydrogen. In the case of hydrogen, we have an accumulative over the time production of hydrogen. In the other case, it's measured at real time. The light and the amounts we use, the hydrogen was detected by gas chromatography, and the other one, the acid formic, was detected by HPLC. We have very good results comparing with another zinc oxide, but to be honest, we are in the bottom of the production of these two fuels because we need another co-catalyst or to use to form an heterostructure, for example, with copper oxide, with a P-type material, or I don't know, maybe ruthenium, platinum. Actually, if we use this technology to perform thin film, and we do this again, but for photoelectrochemical process, in that case, we use a counter anode. So in this counter anode is made or is normally by platinum. So in that case, probably the results were better. But at least I consider I have results interesting. Maybe in the future I will add another compounds in this zinc oxide in order to increase or to enhance the behavior of the material. No? But well, at the end, we corroborate that we have N-type material, well bind alignment of the bonds for to develop these reactions. But I need to add something else to improve the performance. No? This is the team. Doctora Edith Luevano is who made the experiments of hydrogen and photoreduction of carbon dioxide. If you want to work, you can write it, then probably she can help you. If you work with with metal oxides or semiconductors, and you want to do something like this. And well, that's what.
Thank you very much, Dr. Odi, for a nice presentation. So I'm humbly request you some questions if you have. And online also you can raise your hands and you can also ask online people. Yes, okay.
Hola, doctor. Muchas gracias. Thank you so much for your presentation. It was very nice. My question, I have 2 or 3 questions. Like when you are performing the green synthesis process, in the methodology. Yes. Oh, how did you decide the concentration of the orange peak along with your zinc, the salt which you're using?
At the beginning, it was arbitrary. Just looking what happened. It wasn't. The only thing that I took from another for a previous report is the combination of ethylene glycol and water. In that report, I don't remember if they use zinc acetate, but they use 6 salts and this combination of ethylene glycol and distilled water. And they moved the proportions of water and ethylene glycol. They obtained also by microbial reaction, and they obtained different morphology. Actually, they reported close to this proportion. They obtained a morphology like a peanut, a double bottle, like a cacao butter. And that for at least for them, it was the best in the photodegradation process that they performed. But this was not. Another thing that I have to solve at the beginning was the destruction of the phytochemicals, because at the beginning I was using 20% in weight of the biomass. However, it was very difficult to remove it because all the liquid gets absorbed in the powder. So I have to decrease around 5%.
Okay. And doctor, like I'm also working with the green synthesis process, but the problem that I face is like the plant extract or the extract that we are using naturally, they have a lot of, like sometimes the plant, depending on the plants, they have a lot of phytochemicals or these type of chemicals. No, how can like according to your experience, how can we reduce the amount of like chemicals so that the zinc oxide material is more in amount and the components are less, because in FTIR results it a lot of time that like you have also shown in your FTIR results there are any like bondings of carbon oxygen and hydrogen and carbon per nitrogen for the plant extracts, no? So how can we reduce with your experience like
Well, it depends on what is your goal. For example, in my case, I was looking just for morphology, but in other examples, they try to functionalize the zinc oxide. For example, using medicinal or high pulsate plants related to medicines. So I don't know if you are looking for that. But you can probably use something to help you to form zinc hydroxide. I don't know if you use ammonia or zinc or sodium hydroxide, something like that.
Sodium hydroxide for reducing the pH, because sometimes when the pH is high, the material like according to the green synthesis process, as we know, when the pH is high, the salt is more agglomerated, and there is more agglomeration of the salt. So to reduce the pH, or to the pH should be around 7 to 8, to obtain the material's morphology.
You can at the beginning, I would suggest to reduce the concentration of all the reactant. So it will to conduct you to obtain even smaller particles. Obviously, you will. I don't know if you obtain process 2 grams. If you reduce it by half, you probably obtain 1 gram. I don't know if that is a problem for you, but if you, I don't know what is your process. By what technique?
I use the same green synthesis process where I use the extract of the leaves of a plant, and along with that I use salt, zinc chloride salt.
Yes, but the heating process is by
Sorry?
the heating process is by
Heating process is by annealing, like thermal treatment. The heating process is in a hot plate, but later I do a thermal treatment in a substrate for different
well,
temperatures.
if you want to remove only the organics, you can the process of annealing will last more time, or reduce the amount of scrap. That at the beginning, I will suggest that if you want later,
Okay, sure. Thank you so much.
Okay, I think we don't have time, so if we will have some questions or anything, you can consult later, no?
Okay.
So thank you, Dr. Wali, for your. So next, we're having the CCID 29, Dr. Francisco Javier. I think he's presenting from online. So Dr. Javier, can you present yours? The title is Architecture Control of TiO2, graphene oxide hybrids via graphene oxide concentration, balancing adsorption, and photocatalysis.
Hey, can you see my screen?
Yes, yes, we can see you. We can see your presentation. So, Mr. Tan, go ahead.
Yeah, can you see my presentation? Sorry, I didn't hear you.
Yes,
Yeah.
we can see, and you can start presentation.
Okay. Thank you. Okay, good afternoon, everyone. It's a pleasure to be here. And my name is Francisco Javier, and the work I'm going to present today was carried out in collaboration with the colleges from different institutions. And the title of this presentation is Architectural Control of Titanium Dioxide Graphene Oxide Hybrids via Graphene Oxide Concentration, Balancing and Absorption and Photocatalysis. This is the general content of this presentation, and I will start with a brief introduction and motivations. So let me begin with this image. So we see 2 glasses of water. One looks dirty, the other looks perfectly clean. Most of us immediately can think that clean water means safe water. Unfortunately, that is not always true. Even water that looks crystal clear can still contain invisible pollutants, like, for example, emerging contaminants. So this is the hidden challenge we are facing today. So it looks clean, but at the same time, it is not really safe. So when we are talking about emerging contaminants, we are not speaking of one specific or single chemical. We are speaking of a different or variety of substances that are present in our water bodies. So here we can see in this slide some example of these different contaminants, like, for example, dyes, heavy metals, pharmaceutical products, pesticides, among others. So, but something important is what makes these contaminants so challenging is that they often appear in very low concentration, but they can still cause a significant environmental and health risk. Even more, they usually occur together in complex mixture, making removal more complicated. So in summary, water is an essential resource for life on Earth. However, despite the importance of the water for life, it's around 80% of the wastewater in the world is discarded, mostly untreated into river, lakes, ocean, or different kind of water bodies. Of course, we already have conventional water treatment technologies. They have served us well for many years. But today, with the rapid population growth and increased pollution, these systems are reaching their limits. They were not designed to deal with the complexity of the modern contaminants as the emerging contaminants, for example. This is why we need to explore new solutions promising for example, why promising alternative is the use of nanomaterials. I mean, advanced materials with unique properties that can help us to remove pollutants more efficiently, even at very low concentration. So the use of nanomaterials in general has many advantages over the large counterparts. Like for example, with these nanomaterials, it's possible they have large surface area. It's possible to modulate different properties, like for example, optical, electrical, thermal conductivity, mechanical properties, and additionally, they have good chemical reactivity. So when the materials in general are used in water pollution control, they have the objective in general to eliminate or reduce the concentration of pollutants below a defined level to ensure the human health and environmental safety without side effects. So an example of this can be seen in this slide with the use of dyes. Initially, with a high concentration, it's possible to see more coloration, and as the time passes in presence of the nanomaterials, the coloring decreases until it becomes transparent. However, it's important to say that that is not the case for all contaminants, as for many, it is not possible to observe their changes with our eyes, and it's necessary to use a specific equipment for its identification or quantification. On the other hand, regardless of the nanomaterials being used, there are two main phenomena involved in the contamination of water, and they are absorption and photocatalysis. So absorption in general is an exothermic process, surface-based process in which molecules of a compound, in this case the pollutants, are deposited on the surface of of an absorbent, or in this case a nanomaterial. On the other hand, the photocatalysis is a set of chemical reactions involving the acceleration of photoinduced reactions in the presence of photocatalyst or the nanomaterial. Something important to mention is that the first phenomena, I mean absorption, in this case, the pollutant doesn't disappear. It only remains absorbed on the surface of the material. On the other hand, with photocatalysis, the pollutant disappears, or these different pollutants or molecules are transformed into not pollutant molecules. That is the difference in general in these both processes. So one example of these nanomaterials is titanium dioxide. Titanium dioxide is one of the most studied metal oxides due to its ability to act as a photocatalyst using the energy of the light to break down organic contaminants in water. Titanium dioxide has been used to remove different kinds of contaminants, like for example, pesticides, metal ions, drugs, dyes, and even so, it's possible to remove different products associated to different microorganisms. However, there's a limitation with this material because its photoactivity is induced only by the UV illumination, and that is because its bandgap is around 3.2 electron volts, and that means that it can absorb only around 5% of the UV radiation included in the solar spectrum. That is why there are different strategies to modify this material with the objective of improve the efficiency in absorption or photocatalysis. Some examples are surface modification, morphology control, doping. However, in our case, between these different alternatives, we decide to work with incorporation of another material to create an hybrid structure. In this case, we select graphene oxide. So before defining graphene oxide, it's important to define graphene. Graphene is a two-dimensional crystalline allotrope with an hexagonal lattice structure made from pure carbon atoms. In this case, then graphene oxide is the oxidized form of graphene. In graphene oxide, it's possible to find different functional groups that would help us to capture different molecules of contaminants in water. So by the incorporation of graphene oxide into titanium dioxide, the goal is to make the most extraordinary absorption properties of graphene oxide with the outstanding photocatalytic properties of titanium dioxide to create an hybrid nanostructure that improve the efficiency of contaminant removal from water in general. That is why the main objective of this specific work was to investigate the impact of graphene oxide concentration in the architecture of the hybrid nanostructures and their effectiveness in water pollution control by combining absorption and photocatalysis processes. This is the fabrication method we used to create these hybrid materials. In general, the nanostructure were fabricated using an ultrasonic bath in which the fabricated or previous fabricated graphene oxide powder and commercial titanium dioxide were sonificated and then mixed in a solution with ethanol using different ratios of graphene oxide and titanium dioxide. Before showing the next or the following results, I would like to give you a short context. In a previous study or in a previous investigation, we also work with 2% of graphene oxide. But in this case, we change the oxidation degree of this material instead of the concentration. So by the using of different kind of graphene oxide, we obtain different morphologies in the final material or the final hybrid. So 10 images show that the material were mainly formed by titanium dioxide particles coated with graphene oxide, creating a kind core shell structure. So in this case, with lower oxidation degree, we notice that irregular graphene oxide shell with different thicknesses ranging from 6 to 21 nanometers, in addition to some uncoated sections in the surface of the particle. Additionally, the nanostructure with highest oxidation degree, the graphene oxide show more uniform shell that completely coat the particle, albeit with the reduced thickness. This organization in general was influenced by the initial morphology of the graphene oxide. That is, the graphene oxide with lower oxidation degree show larger carbon platelets as well as greater stacking compared to graphene oxide with higher oxidation, where there is a higher degree of flaking and wrinkling due to the exfoliation or incorporation of functionalities inside of this material. When evaluating in detail the contribution of each phenomena, we observe how the nanostructures with lower oxidation degree demonstrate less efficiency in absorption. As we can observe in this, the efficiency in absorption is poor, and but the greater efficiency in photocatalysis if we compare both phenomena. On the contrary, with higher oxidation demonstrate better absorption but lower efficiency in photocatalysis. So in summary, we notice a clear trend. Whether the oxidation degree of graphene oxide increases, the absorption performance improved, but at the same time, the photocatalytic efficiency decreased, as we can see in this trend. Based on this, with the graphene oxide that show the best results, I mean the first option, TU1, in photocatalysis, we decide to modify the graphene oxide concentration, studying the behavior at different concentrations, in this case 2, 5, and 10% of graphene oxide. So in this slide here, we can see how the morphology of titanium dioxide change when we increase the concentration of graphene oxide. The first image corresponds to the hybrid containing just 2% of graphene oxide. And as we can observe, the particle or the titanium dioxide particle is partially covered by graphene oxide sheets. So when graphene oxide concentration increase, we can see a clear transformation, and we can observe how there is a modification, and now the particle is totally covered with this graphene oxide. For example, when we increase the concentration until 10%, we can observe how there's agglomeration of graphene oxide, and the kind of the core shell structure is not defined comparing to the two first examples. In this case, I would like to show you super quick this, a low concentration. We can observe the evolution, and based on this, we can propose an hypothesis where even with higher graphene oxide concentration, there is an evolution of the system into typical structures reported in the literature, where the larger graphene oxide sheets add as a support and titanium dioxide nanoparticles are distributed on their surface. Now we can connect these different results and we can observe how in general, for example, with low concentration of graphene oxide, we can observe less absorption. However, when we increase the concentration of graphene oxide, we see at the same time more efficiency in absorption, but at the same time the photocatalytic activity decrease in this as a function of the concentration. Just to say, let's look at why 2% works best, and that is because in this structure, the graphene oxide shell absorbs the visible light and becomes photoexcited, and this means that the electrons are generated in graphene oxide, and then they move to the conduction bank of titanium dioxide. And so once the electron reach, they can react with the oxygen molecules and uncoat surface of titanium dioxide, producing radicals that break down the dice molecules. And at the same time, graphene oxide helps us to absorb the dice molecules, bringing them close to the active sites where the reactions happen. So on the other hand, when we increase the concentration, under visible light, the graphene oxide still absorbs light, producing electrons, but however, this electron can move toward a titanium dioxide core, but now the titanium dioxide surface is completely closed by the graphene oxide layer. And because of this, the electrons cannot reach the oxygen molecules in solution. And so the radicals cannot create these radicals efficiently. As a result, the photocatalytic activity goes down, even throughout the structure looks perfect. And finally, with 10% at this concentration, the structure is very different. Under visible light, graphene oxide absorbs the light and can produce electrons, but the structure is dense and dark, and the light cannot reach most of the titanium dioxide particles.
Francisco, un minuto, porfa.
Okay. Yeah, I will finish. And okay, just with this, the electrons are generated, get trapped inside graphene oxide, and recombine instead of the moving titanium dioxide. And additionally, titanium dioxide particles, they are not covered by graphene oxide, simply don't react with visible light because titanium dioxide alone cannot only work under B or UV, but it can work under UV illumination. And to finish this presentation, I would like to give you a short summary of the main conclusions. And I would like to say that the nanoscale architecture of these hybrids is strongly governed by the graphene oxide concentration, leading distinct structural configurations from partial coating to full encapsulation. And something additional I would like to say is that the optimal performance arises from the balanced titanium dioxide and graphene oxide interface that maximize the charge transfer while maintaining accessible photocatalytic sites. That's all for the moment in this presentation. If you have any question, this is my email if you have any additional question in the future. Yeah.
Thank you. Thank you very much, Dr. Francisco, for sharing your research work. So we have one or two questions, if you have, please. From online also, you can raise your hand and or you can write in the chat.
Yeah.
Okay, we have.
What's the color of the material? Because I know that the titanium dioxide is color white and is the one that is used for impermeabilization and also the wood paint. But I have the curiosity, what's the color of the
Composite.
composite, the TO.8.
And did you hear?
So, sorry, I cannot hear correctly.
Okay, what is
I'm
the
not sure if
color
the
of?
question was about the color of material? That was the
Yes.
question?
What color of the composite material?
Okay. Yeah, in this case, yeah, titanium dioxide alone is white. In graphene oxide, we noticed some changes. The color was different according to the oxidation degree, but for this specific work, the graphene oxide we used it was a dark color. And as a consequence, the hybrid, it has a gray color for this specific material, because according to the oxidation degree, we notice changes in the coloration, and that is why there was some changes, but in this specific is gray color.
Okay, any more question? One more?
I have a quick question. The whole target of this is, I think it's to remove contamination components from water, isn't it?
Sorry, I'm confused with this question. Could you
Your,
repeat it?
your work is based on to remove the water contaminants, right?
Yeah.
Okay, which one of the functions, absorption and photocatalysis, was the most important one to achieve the target of this study?
Okay.
Which-
This.
Yeah, go ahead.
Yeah, it depends the objective we want to reach with this procedure in general. For example, it depends of the kind of contaminant we want to remove from the source of water. For example, there are some contaminants that generally it's more easy. It's easier to remove by absorption process, but there are other contaminants that are easier apply photocatalysis and degrade them. But in general, it is going to depend of the target contaminant we want to remove from the source of water.
So different contamination needed different functional groups?
Yeah, because of the affinities of these contaminants with the material. It will depend of the other factors. Yeah, but in general, we can say that, something like that.
Okay, so we don't have time. So thank you very much for your time, Dr. Francisco. So next, we're going to continue with again Dr. Wadi with the CCID 154. The title is Development of Membranes Based on Recycled Polyethylene Tariff Plates, functionalized with zinc oxide, graphene oxide for the removal of methylene blue by absorption. Please go ahead.
Thank you. Well, I ordered in this way the presentation because I'm going to use, or I use the zinc oxide that previously showed you in the last presentation, but in this case incorporated in some membranes that we fabricate by using PET from plastic bottles. This work is done by some students in Chiapas or Unicach. So the credits are for them. This is the content of the presentation. I'm going to talk about the membranes, how they work, in which the application we use, the methodology process to fabricate these membranes, and finally the results and the conclusions. Well, this is a very short work. It's the first work that we are trying to abort this new technology, at least for us, in the group that we are trying to form. So the work is very, very simple, but it shows that it has potential. Probably the results are not very good, but with these students we have improved, and probably in the future we will publish these results with another materials. Again, we know about the problems related to the presence of different contaminants in water and the great consumption of water by the different industries. In case of textile, in the agricultural, they have a lot of pesticides. And in the automotive zones, they give free a lot of metallic compounds. So we have a huge problem. Actually, Conagua in Mexico, for the specific case in Mexico, they have found different places. You can see in the map, the red one. These are the places that has greater contamination in the water basins. In Spanish, las cuencas más contaminadas de México son las rojas. So if you see it, they are located where the industry regions are located. So it is a coincidence. So they have this kind of pollutants, heavy metal, pathogens, a lot of recalcitrant organic compounds. So we have something to do related with this. I am from Mexico State. I studied during my licenciatura. I don't remember. I studied very close to the Lerma River, around 5 kilometers away from the river. And believe me, the smell of the river is very hard. So the people who live close to these rivers, it's very, even if you go travel around the river in the car with the windows up, you can smell the odors of the river. So it's very hard. Well, the proposal is to reuse PET bottles. This is a product that is produced in this way, between 30 and 40 millions of tons in global, and only 10% of this material is recycled. In the case of Mexico, we have close to 1 million, but we have a very high percentage of recycling, which is close to 74%. Actually, in Mexico, we have some factories in Monterrey, for example. They use the bottles to produce another new bottles, or even we can produce some textile for like shirts or things like that. So the idea in this work was to reuse the plastic bottles in order to produce some membranes and use it by filtration and to remove pollutants from water. Why we use PET? Well, the PET is this block of elements. So this is repeated a lot of times to form a big chain. According to the number of these blocks, it gives different properties. In the case, for example, in the plastic bottles, it is around 200 blocks of this one. For example, in the case of the garbage bags, they are around 100 and 150. And for example, bottles of high density, like that we use for the water of 20 liters, they are chains of around 300 blocks. So we have a lot of waste in all Mexico, so we can use it. And basically, the idea is this: to form the membrane and to pass the water through it in order to achieve clean water. But also, not only by filtration process, we can or we want to reuse the materials that we have developed before in order not to only filtrate, but also to absorb the pollutants. Actually, the original idea was to mix three things: absorption, filtration, and photocatalysis, because zinc oxide presents a photocatalytic effect. However, when we incorporate the photocatalytic process, the process was very unstable. I don't know if you know, but when you do a photocatalytic process, first you study the absorption process. Once you reach the equilibrium state, you light on the lamps, and the photocatalytic process begins. So when we turn on the light, we observe that we have desorption of the dyes from the membrane. So at the end, the result was were poor or lower than only by absorption or filtration. Well, filtration is only governed by the porosity. The size pore defines which things pass through the membrane or not. So the bigger things that pore size wouldn't pass through the membrane, and the smaller one will pass. Another aspect are the hydrophilicity and hydrophobicity. and the surface morphology, but this process is mainly governed by porosity. Once we add some materials in the membrane, for example, graphene oxide or graphene-based materials, carbon, we introduce some organic functional groups. It promotes absorption of different species. For example, if we add some negative functional groups, we can absorb or catch some positive compounds. For example, if we use negative, we can attract a positive like methylene blue or malachite green. And another interesting thing is that, for example, if we add some metals like silver or copper, we can promote an antibacterial activity. So when the cells of these pathogens reach the metal compound, the membrane is destroyed. So the organs inside of the cell are sent out of the cell. So the cell at the end is killed. Another interesting aspect is that if we introduce some semiconductors, for example, zinc oxide, we can promote photocatalysis and absorption, but also we give some electrical properties to the membrane. So, for example, if at the end of the process of filtration and absorption, we have the membrane and it is conductive, we can introduce some current with certain potential. We can perform reactions over the membrane. So at the end, we can clean the membrane by applying this potential of this current. So we give another reuse to the membranes. So that's a reason that why this is very interesting. This is the process that we follow. It looks very complicated, but believe me, it's very simple. We have 3 bakers. That is the reactants. PET is the base. Then we have phenol. Phenol is the thing that dissolves the PET. And polyethylene glycol. This polyethylene glycol gives us the porosity or controls the porosity in the membrane. And at the end, we have ethanol just to clean the membrane. In the baker A or in the process A, we have some part of phenol that is heated. One is liquid. We introduce some slides of PET. They are put in 1 per 1 centimeter. Once they are dissolved in the solution, we mix it with a second solution. In this, again, we heat phenol in order to become a liquid. Then we introduce the polyethylene glycol, and at the end, we mix these 2 solutions. During the mixing of these 2 solutions, we prepare a third solution, the baker C. In the baker C, we heat phenol. For example, when we only want to produce some membranes with PET, we only heat phenol. If we want to introduce another material, for example, zinc oxide, at this moment we mix these 2, the liquid phenol with the zinc oxide, and at the end we mix the combination of A and B with C. In this vessel, we introduce a glass like this one, in order because it is very flat. So at the end, we introduce all the solution in the glass, and we add before some ethanol in order to facilitate the removal of the membrane from the glass. The ethanol is evaporated by itself. These are the results. PET and PEG are not crystalline materials. They are amorphous compound. So that's why we see this signal in the XRD. As you can see, we don't have a zinc oxide signal because it is only PET. This is the membrane of PET. And in the case of the membrane with zinc oxide, we have an increase in the crystallinity of this part of the diffracted of the last one. I don't present the other one because the zinc oxide has a very high crystallinity. So if I put it with this will be lost because it is amorphous. So it wouldn't be in the plot. So this is the infrared spectroscopy. I don't know where it's in just a bit, but these are the different functional groups that are in the membrane. This is the membrane only with PET. If you see, it's more or less the same signal when we introduce the zinc oxide. We don't have big changes. Only we have a small change here. Actually, in the previous report, we observed the peaks below to this. And actually, the signals or the peaks associated with graphene oxide more or less are the same that these peaks. That's what we see more or less the same signal. This is the same of the membranes. As you can see in the first one, it is flat. There are no porosity. And when we incorporate zinc oxide, we perceive some kind of holes, no? Even porosity to the membrane. By EDS, we observe that the presence of zinc oxide, which is around at the end around 32% in mass into the membrane. This is the process that we follow for the filtration and filtration absorption process. We use only 15 milliliters of methylene blue solution with that concentration and all the time in that conditions. As I mentioned before, we tried with light, but it was a very poor effect. So when all the solution is filtrated, we use a spectrophotometer in order to see how much of the methylene blue was removed. In the case of zinc oxide, not all of the methylene blue was removed, so we have to do some cycles to reuse the same membrane. These are the membranes. The membrane, as you can see, only by using PET is almost white. At the end is the color that's absorbing the membrane. And when we use zinc oxide, the membrane is a little gray, which is the color of the zinc oxide that we synthesized in the previous work. As you can see, also the dye is absorbing the membrane. These are the results. As I said before, this is the first approach of we have with this kind of technology. The results was not like we expect. Actually, in the first process by filtration, we achieved almost all the removal of the dye. In the other case, we have to perform even 9 cycles in order to achieve this response. The only thing that it was better for the membrane with zinc oxide is the porosity. The process by this one it was around 2 hours, and in the other case, the process was almost the same. It was 2 hours and 20 minutes. So we have maybe not the best results. With this result, we are now incorporating new materials, for example, biochar or biochar activated. And with these materials, we have observed better results than when we use only PET. Another interesting thing that we have observed is that when we store our membranes used with the dye in some Petri box and we leave it in the laboratory, at passing the time, these membranes can be cleaned by itself because of the presence of these particles. But this is something that we don't report. And this is part of the team. These are the 2 students that were working with these membranes. And they were supervised by Dr. Rosillo. And that's what.
Yeah, thank you. Thank you very much for your clear presentation. So we have one questions. We have time, please. If you have any.
What is the porosity of you? The porosity is very complicated to measure because I try to do a bed. Yes, but when we hit the well to measure bed, you have to hit the what you want to measure. So when you hit the membranes, they become some liquid. So it's very complicated to measure. We have to use another technique. We expect to work with a colleague in Chiapas also. They use, I don't know if you have this technique in which you have some surface and you place a water, a drop, and according to the angle of the attack, you can estimate by a simulation process the porosity of the membranes. So that we are trying to establish a collaboration with.
And the other question, how long how long is your process? For example, you filter, I don't know, 1 liters of water. How long is the process?
The process of filtration.
Yes.
It's here. It's 2 hours. For filtration, it's 2 hours. For only
What
one
volume?
only one cycle. The volume was 15 milliliters.
2 hours or 2 milliliters?
No, for 15.
15 milliliters. Yes. Thank you.
Okay.
What
Thank you.
kind of degradation have you observed in the membranes, the two types? Some uses, what?
Actually, we have some troubles with the stability of the membranes. If they are in liquid water or things like that, they can keep working in the time. But if you leave it in a dry condition, they start not to grow, but they some fractures are visible. So if we would like to reuse it, we have to store it in liquid condition.
Okay, I think any more questions? Short question. Okay, if we don't have, so thank you very much for the presentation. So next we organize as the CCID 162, which is going to present by Eduardo Ramirez Martinez. So the title is Influence of precursor milling time on the photocatalytic performance of zinc oxide thin films in methylene blue deposition. Okay, the last one. Es que había dos sesiones. Sí.
Go ahead. Okay, my name is Eduardo Ramirez. And today I will present the work entitled Influence of precursor milling time on the photocatalytic performance of synoxide films in methyl blue degradation. Made in collaboration with Gabriela María Marrón, Eduardo Service, María de la Luz Blanco, and Ángel Eduardo Zamora Suárez. Okay, so heterogeneous photocatalysis is an environmentally friendly technique. Technique that allows the degradation of organic products using ultraviolet or visible light without producing by enhanced by products. Among the most studies for catalysis, zinc oxide as semiconductor we stand out to its wide band gap, high stability, and low cost. However, the photocatalytic efficiency of zinc oxide strongly depends that the production the beneficiaries depends in structural, optical, and morphological properties, and which can be modified and synthesis conditions. In this work, we focus on how the milling time affects those properties, and consequently, the photocatalytic efficiency of zinc oxide decreases. Okay, zinc acetate anhydride well-prepared precursor at a concentration of 0.2 mole and mechanochemical one in a planetary mill at 300 revolution per minute for different times, 15, 30, 40, 45, 60, 120, 140, and 300 minutes. Okay. The dim films were deposited on glass substrates at 475 degrees Celsius with a rate flow of 1 milliliters over minutes, a fixed deposition time of 5 minutes. Okay. Using the pneumatic pyrolytic strike technique. Other way is the thickness of the dim films varied between 400 to 1,100 nanometers, depending of the milling time. The nomenclature used is its materials inside lower is milling time and sorry, it's revolutions and milling time. Okay, diffraction partners confirm the widths, the good side type hexagonal structure with the preferential orientation in the 002 plane. The crystal size calculated using Schrödinger equation increased with milling time maximum to 31 nanometers at 45 minutes, indicating improved precursor activity. Subsequent milling time longer than 120 minutes. 20 minutes after this time. So generates defects and
crystallinity, reducing structural. The dislocation density decrease markedly in the 30 to 60 minus interval, reaching its minimum at 30 minimum minimum it's okay for sinusoid milk at 45 minus at 1.04 by 10 to the minus 3 nanometers to the minus 2. But while the strain lattice decreases to 3.79 by 10 to the minus 3. The C over I ratio remains close to in the ideal value. It's 1.63. Confirm the structural stability of synapse. To find same images show exhibit evolution morphological with increased milk time. Then films obtained with milk precursor exhibit will define hexagonal grains. Other case is it's between 30 and 16 minutes grain growth and a large surface area was observed with an average size close to 500 nanometers. However, for larger times, the grain size decreases dramatically. Reducing el grain size. APM images revealed important difference between the samples. In question, surface roads. The synoxide 68 sample show which exhibit the a smaller surface and low roundness and round rounds. With the sample show the lowest photocatalytic efficiency. In contrast, synoxide 45A sample show highest surface roundness, exhibit the highest photocatalytic efficiency. This behavior confirmed when previous studies which report that increased roundness can enhance the absorption of reactants and promote electron hole separation, which are beneficial for photocatalytic reaction. All the things report, we can see high transmittance in the visible region with absorption H around 365 nanometers. The optical band gap calculate using a TOC method range between 3.23 at 338 electron volts. Showing a slight blue sheet in the intermediate samples associated with a lower defects and showing red sheets at lower and larger times due to disorder structure. The efficiency for photocatalytic was evaluated by the degradation of methyl blue dye at a concentration at 1/10 to the minus 5 mole in aqueous solution under 232 nanometers. Kinetic analysis that show that the process follows pseudo fixed order kinetics with rate constant values between of 0.05 to 0.356 hours to the minus 1. The zinc oxide 45A excited the best photocatalytic performance. This sample achieved approximately 45% the methyl blue degradation on the intermediate irradiation. In contrast, zinc oxide 68 showed the lowest degradation efficiency with 43% degradation in 3 hours under ultraviolet irradiation. This result confirmed that the moderate roughness and grand size are beneficial factors the efficient production and transport for photoinduced currents. We can see the values these samples and on thin clips. We can see the solutions, initial solutions at 3 hours, 0 hours, sorry, with concentration methyl blue. After initial solution, the sample initial for photolysis and the two samples with lowest efficiency and maximums. In conclusion, by varying the milling time of the zinc oxide precursor, the grand size, crystallity, and the effect density of zinc oxide films, as well as their Roche porosity, are changed, which directly impacts photocatalysis by balancing the ability of active sites with charge recombination. Intermediate milling 45 minus delivery, the best balance between crystallinity, exchange rate, crystalline size, approximately 31 nanometers reduced this location density structure. Surface morphology, higher grain connectivity with moderate roughness and optical properties, interval band gap, the highest photographic efficiency under ultraviolet irradiation and operating condition sample synoxide 45 HV. Approximately 75% methylene blue degradation in 3 doors and the largest rate constant approximately 336 hours to the -1. Xavier, in comparison with the sample synoxide is 60 m. At no blemish, here the persons support technique. Thanks.
Thank you very much, Eduardo. So we have one question for the time. So if anybody from online, you can also ask by raising your hand. Okay, if not, like I have one short questions. How you compare this work with the published work? How do you compare your results compared to other published works?
Okay, our study demonstrates that mechanochemical treatment of the precursor prior to deposition relationship direct mechanochemical activation, structural crystal structure, and of photoactive performance. Something that has been lower explored and in Paleolithic style paintings.
Okay. Okay, thank you very much. So we can. Before starting the next presentation, we have another news that after this presentation, we are having one more presentation, which from the Anglo session, but they seated to here. So please, I request you to, if you can stay one more presentation now. So the last presentation, my second last presentation, we are having again Dr. Odimba is going to present. The title is eco-friendly bismuth vanadium oxide photocatalyst via orange field mediated solvothermal synthesis application in gas to production and CO2 conversion. Go ahead.
Thank you. Well, this is a similar work that I previously presented zinc oxide, but in this case it's more complete and it's a little more sophisticated because in this case we want to, I'm going to present the synthesis of a ternary component. In the other case, the zinc oxide was very easy to synthesize only because of the presence of the ethylene glycol. This is more or less the content of I'm going to talk. Instead of microwave radiation, I'm going to talk about solvothermal synthesis process. Again, about green chemistry and the synthesis process of the bismuth vanadate and the results and conclusion. Well, again, we know about the pollution of water and the environment related to the use of fossil fuels and the greenhouse gas emissions. So we have to do something. Photocatalysis is part of a thing which can help us to solve this kind of problems. Just following the first presentation, as I mentioned before, zinc oxide works as a photoanode, promoting oxidation reaction. This is the reason. We have the two bands. I don't know if you have worked with union PN and how the band bends when the two semiconductor reaches. In this case, and this explains how the behavior of the semiconductor. For example, we have the two bands, conduction band and valence band, and we have the Fermi level. In a union PN, electrons from the N-type material goes to the P-type material, and holes from the P-type material goes to the N-type material, giving a positive charge to the N-type material and negative charge to the P-type material, creating electric field. So it works like a valve, like a direction the flow of the current. In a solar cell, for example, the photoelectrons generated goes from the P-type, from the absorber, to the N-type. In this case, it helps us to explain the behavior of the semiconductors. For example, in this case, we have an N-type material, like a zinc oxide or like this material, and the potential of the reduction or of oxidation of the material. So in this case, some electrons goes to the electrolyte, and some holes of the electrolyte goes to the surface of the material, promoting this bending. So we have a positive region in the semiconductor. So we are going to attract the electrons from the solution. In this case, for example, from the pollutant or from the water if we produce hydrogen. So what we are performing at the end is an oxidation process. That's why N-type materials, its behavior is like a photoanode promoting oxidation process. In the contrary, if we will have P-type materials, the bands will be moving to the other side. So, and we'll explain how it is constructed a P-type material behaves as a photocathode or as a performing reduction reactions. Well, why I'm interested in green chemistry. I want to not to use chemicals that are difficult to handle, for example, acids, or something that are toxic process in which you can create hydrogen and atmosphere that it's hard to complicate. For example, in the last year, I know that something explodes in the lab. So I don't want to, or I don't like to work with that kind of things. So that's why I use this kind of process. The potential of the orange peel I mentioned before, but in this case, we are not only performing giving a shape to the particles. In this case, we are synthesizing a ternary material, because if we don't have components or agents that produces this kind of material, at the end I will only to obtain two oxides, bismuth oxide and vanadium oxide, and I'm not looking for that. I'm looking for bismuth vanadate. So that's a reason why this is very important. Well, in this case, this photocatalyst has three structures, two tetragonal and one monoclinic. The monoclinic is reported to have the best photocatalytic performance. The band gap is around 2.4, and so it means that it works with invisible light. And the bands are favorable as an anode to promote oxidation process. In this case, to produce oxygen. And just an equilibrium process, it has to produce an reduction reaction. So in this case, for example, carbon dioxide reduction or hydrogen evolution. The materials has low cost and are abundant, so it's not we are not working with expensive material. The process is very simple and similar to the zinc oxide, but in this case, I'm working with an autoclave. In this case, we have the same extract. We add these two sources. It is bismuth nitrate and this source of vanadium. In a conventional synthesis, we will, like this one, but not using a strap, we will use some auxiliary agents to promote the meeting between bismuth and nitrate to generate the thin phase. But also we will need something else to dissolve these two salts. It is reported that they use nitric acid to dissolve these two sources. I don't need it, not need it to in this process. I just use the strut and those two sources. Once these are not dissolved but integrated in the solution, we place it in an autoclave under this condition, and at the end we follow the same process. We wash it by centrifugation, and we dry it, and we obtain the powder. The powder is also a little brown with green color because of the material is yellow. So at the end, when we anneal, it becomes from brown to yellow color. This is the results. For example, in XRD, it's very important because we obtain only the monoclinic phase. We don't obtain signals or things related to the other phases. So it not only the stress not only help us to obtain a pure bismuth vanadate phase, but also with the monoclinic structure. We estimate the band gap by using the duplex diffuse replicants. And as you can see, the band gap is more or less close to the reported in the papers. And at the beginning, I was expecting that I had something similar to the zinc oxide. I was expecting to have graphene oxide. But in this case, I didn't use radiation. So the heating process is by convection and conduction. So I didn't obtain the signals of D and G related to the graphene compounds. I only see the characteristic peaks of bismuth vanadate related to the bonds between bismuth, vanadium, and oxygen. And that is reported in the literature. In this case, it's the infrared spectroscopy. In another work, we are working with different temperatures. But the important here is that we observe the presence of different functional groups, but they don't have we don't observe the signal in Raman. So we cannot associate it to the presence of graphene oxide, but we have graphene bismuth vanadate functionalized with these functional groups. We perform XPS. This is important because of we can estimate the presence of different groups, functional groups, by making the convolution process. And we can corroborate the oxidation states of the different elements that form the material, bismuth, vanadium, and oxygen. They are similar to reported in the literature. These are the morphology. It's the same as TM of the material. This is the anneal material, and the anneal material at 350 Celsius degrees. As you can see, not a lot of changes are observed in the morphology. The only thing that we see beside the change in color is a little cracking and removal of the organic content. If we increase, we observe an increase in the porosity in the surface, but actually in the bed, we observe a decrease in the surface area. These compounds are formed by different nanoparticles around 10 nanometers in size. Another way to prove that we have the ternary phase of the material, we perform elemental mapping of the material. And as you can see, the elements are well distributed around all the compound. So we don't have focus only in one region bismuth and another region vanadium. We have all homogeneous elements. From this is the field method, photoluminescence. This is just to prove that which is the best sample to transport electrical. Which sample has the best condition to transport electricity, no? Or which has better electric properties. The best, obviously, is the which has the lowest signal is that is not annealed. However, it floats on the solution, so we cannot use this material. Once we anneal, as we increase the temperature, the signal increase. So it means that we have less transfer properties of this compound. So at the end, we only work with the best one, the red one, that is related to this temperature. And also we perform electrochemical characterization in order to see what is the conduction bands in this case, because the slope is positive. So we have intact material with the slope. This value is this value. It will be higher. And with the band gap, we add and we found the other one, the balance band. So the reaction or the potential of the reaction that are inside of the gap, they can be performed. In this case, is this one. But again, as I said previously, we can do these two reactions, but the material is an N-type material, so it promotes oxidation reactions. These products are made by reduction process. So at the end, it is produced for more complex mechanism or process, because at the end the reaction has to find an equilibrium. For example, in water splitting, we form oxygen with bismuth vanadate. Obviously, we have to in some way, I don't know what, but we have to produce hydrogen. We cannot only produce oxygen. So we will have the other one. And as the other one is in a more complex way, it controls the velocity of the speed of the production of this material. So in order to enhance the performance of this material, I need a p-type material also, or an heterostructure. The process are more or less exactly the same that to the previous presentation. It's accumulative in the case of hydrogen, and in the case of CO2 is based on time. And we use this amount of catalyst and these two lamps. This is conditions are set by the Doctora Edith in Nuevo León, so I cannot control this kind of conditions. They use this. And the performance is, in the case of hydrogen, it's more or less the same that I reported for zinc oxide. But in the case of formic acid production, is smaller. Probably it's related to the band alignment. It's more complicated in this case for this material, is to promote this reaction, because the material is more complex to form hydrogen. In the case of hydrogen, we only need 2 electrons to the proton. In this one, we need more. For example, another thing that we can produce from carbon dioxide are methanol, some aldehydes, but are related with the ability of the material to give electrons to the carbon dioxide. So that's the reason it's very complicated to obtain solar fuels. Well, at the end, we obtain this ternary process just by using the extract of the phytochemicals of orange peel powder. It's a very good approach. So in the future, we can mix it with another materials, and maybe in the same beaker in order to obtain composites, or using in another ways to form some heterostructure. Heterostructure would be better in order to have something else, a p-tag or a catalyst here, in order to enhance these two reactions. Well, the bind alignment is correct for the oxidation of water, but is deficient for these other two reactions. This is the team. Doctora Edith Lovano is to perform the hydrogen carbon dioxide photoreduction. And well, that's all.
Okay, once again, thank you, Dr. Modi. So, any questions? Okay, I think this time we don't have any questions, so we can plan also. So, once again, you can see. So, as I said, so I think here we have Miguel Castro, no? Miguel, can you hear me?
Yeah, I heard you. It's okay. I have it in Proclamo now. You listen me? Do you listen me, please?
So you can present you can share your screen.
In this moment, I am in blockout, energy blockout, but it's possible to write the presentation. But I need to log out my pictures. Yes, it's possible. I will share it. I will share in the presentation.
Yes, please. Can you share?
All right, I go. Please tell me if you see my presentation. My pictures.
Yes. Can you in presentation mode?
I am going to begin in
Yes, please go ahead. Go ahead, please.
Go ahead. All right. Well, good afternoon, everyone. My name is Miguel Castro Fernandez, and I will present this paper on behalf of the group of specialists from Cuba, Mexico, and Spain. The energy transition strategy for Cuba toward 2030 has established as an objective in the electrical sector the integration of more than 2,000 megawatts of photovoltaic system for energy generation into national electric power system. Therefore, the analysis of international experiences and the still limited national experiences in relation to the PVS field that have been in operation since 2013 on the behavior of this installation in the face of natural phenomena such as hurricanes become an important element to carry out a sustainable program in this direction. The large-scale introduction of renewable energy source replacing fossil fuels is presented as an essential piece of the energy transition at the international level, and one of the ways to combat the effect of climate change. But in Cuba, it goes beyond the issue since it's a condition of survival, given the need to eliminate as much as possible the use of fossil fuels in energy generation. Given the current problems of obtaining fossil fuel for Cuba power plants, as well as it will be their way to contribute to reduction of the strong pollution that this fuel contributes to the environment. Hurricanes are characterized by the destructive force comprised the strong winds, heavy rains, and storm surge. Coincidentally, regions prone to hurricanes, such as Cuba, are also more likely to receive abundant sunlight, making them ideal graphic area for the benefit of solar panels. Hence, the need to understand whether the presence of hurricane can be a significant concern for the installation of solar photovoltaic energy system. There is experience of categories 3 hurricanes that have caused disastering of photovoltaic solar park, such as one shows in the slide. This implies that in areas where hurricanes are of different categories might be present, panels and components must be selected that meet the industry standard to withstand the possible level of wind, while local building codes must be taken into consideration. Experience has shown from examples such as the one showing in the slide that the secure mounting of solar panels is crucial, and properly designed structure must be used to ensure that the components are firmly attached with resistant elements, either to the root or the grounds, to prevent them from being detached or damaged during the hurricane. The wind load test can be used to assess weather components within the module, including solar cells, interconnecting tapes, and or electrical links, are susceptible to breakage or weather fixed parts. For example, brackets, clamps, screws, fixed hull are likely to fail due to the uniform mechanical stresses occurring during severe wind loading. Example of how tests are carried out on photovoltaic panels is presented in the slide. The use of proper reinforced anchorage and mounting system is vital to strengthen solar panel installation against the powerful force exerted by hurricanes. Reinforced mounting systems, such as hurricane clips and additional support brackets, provide increased strength and durability. Implement these measures significantly reduce the risk of structural failure of panel detachment, ensuring the longevity of the solar panel system. In general, there are some measures that are considered important to prevent the destruction effect of strong wind on solar panels, including solar panels that can be subject to a strong wind must be of high quality and durability. Installing flexible solar panel system constructed from injection molded polymers and made from fiberglass reinforcing nylon is a good solution for the PV field that will be exposed to hurricanes. Using bolted studs and solidly constructed solar frames allows the solar panel to withstand enormous split of lift force. Examples of this effect of hurricanes in PVS system have been reported in the lecture in region. Those are affected by the large number of hurricanes annually, similarly to the Caribbean country, in addition to having a large number of solar installations in operation. For example, in 2012, when Hurricane Sandy hit New Jersey this year, the solar installer reported only 200 panels are a minor issue due to flooding, with very few reports of PV panel damage from strong winds, demonstrating how little impact hurricanes have on solar panel performance. In 2017, when Hurricane Maria struck Puerto Rico, even at wind speed of more than 288 kilometers per hour, a large number of solar panels remained operational as 100% capacity. For example, the PVS system located at the San Juan Via Hospital remained functional through the storm. In 2017, Hurricane Irma struck different countries in the Caribbean region. For example, in the PVS system in Antigua, survived Hurricane Irma without major damage or failure. Haiti solar PV plus battery storage microgrid survived in fact after Hurricane Irma passed through, but however, in St. Thomas, the 4.2 megawatt State Dono solar farm was destroyed. Another example we can see, for example, in 2018, in North Carolina was devastated by flooding when Hurricane Florence hit. Many fossil fuel plants had to shut down for months, but solar power plants were able to resume operation after a few days. In 2022, Hurricane Ian hit Florida, Gold Coast as a Category 4 storm. But Baco Ranch, a little town in this area, no had problem. The PVC dye is designed to withstand a Category 5 hurricane in this town. The solar energy infrastructure is maintained power at Baco Ranch during hurricane, while surrounding community lost electricity. Finally, another study of 50,000 PVS system from the National Renewable Energy Lab in the United States revealed that they hold up during hurricane. In fact, solar panel generation system affected by the effect of poor performance as very few, only 0.1% per year. In 2017, Hurricane Irma struck Cuba. The effect of the national electric system was significant. The generation load balance was interrupted, and the entire system went down. In other words, the entire national grid was lost. The report of the National Defense Council noted that the damage was fundamentally in the distribution system where the PVS systems are connected. The next restoration process involved today the creation of energy island, where I subsequently merged. These islands are formed for distribution energy source, including more than 900 megawatts of PV system already in operation, 40 of which have an installed capacity of 21.8 megawatts. For this reason, the analysis and experience that have been carried out or obtained in Cuba in this regard are highly relevant to the current development of photovoltaic energy in the country. The typical configuration on soil of the PVS system in Cuba is the location of the panel of 15 degrees with respect to the horizontal and north-south direction, with zero azimuth. A graphic example of this configuration can be seen in this slide. A study on the effect of wind on the row formed by the support tables of the panel in the wind tunnel were carried out by specialists from Cujay in conjunction with Uruguayan specialists. These studies show that the separation between rows, considering 2 and 3 meters of separation, the highest pressure value were obtained for the first row, which offers protection to the second and third rows, independently of the separation analysis. Also slightly that the highest value were obtained to the edge for the first row. However, if this separation is only 1 meter, where the edge of the panel of the second row being too so close are submerged in the separation wake in the boundary layer of the first row. Taking into account the typical localization that the panel can have within a row arranged in the PVS system, which can be observed before the conclusion presented in the slide. As a summary of the wind tunnel experimental study, it was concluded that the wind pressure values on a PV panel depend on the relative position of the panel within the tunnel and decrease when located behind the first windward row. The first row of the part provides a shielding effect of the remaining rows in both wind direction analyzed, and this shielding effect decreased as the spacing between rows increased, which is consistent with the international studies. Another study, in this case to evaluate the possible risk for the PVS system located in the western part of Cuba, and which coincides with the region where most hurricanes passed, was carried out. To estimate the level of risk, the general risk equation was used, where the risk is expressed as the product of the probability of occurrence of hurricane of different categories by the vulnerability to the force of the wind corresponding to each to them. And as conclusion, the total expected annual loss due to the strong winds that accompany hurricane are approximately 4.3% of the PVS value, considering that the assumed annual loss due to panel deterioration, which as a surface like 25 years, is 4%. The estimated annual losses due to this natural hazard are comparable to these losses, which is a positive factor in favor of the construction of photovoltaic solar parks. Finally, from a practical point of view, an incident experience was reported in Cuba regarding a PVS system on the construction during Hurricane Ian, which hit the island with Category 3 storm wind. This hurricane passed less than 80 kilometers from the construction site at the time, based on photovoltaic solar park. The construction site was using a high-density support structure system called PG, low profile and certified by the wind code of 289 kilometers by hour. The PEG ultralight low profile racking system has been able to comply with very aggressive wind code and has been certified by the Institute for Industrial Aerodynamics from Germany to withstand up to one exceeding 280 kilometers by hour. The slide shows the profile of the structure in the field. So example on the assembly is this type of structure. But it's necessary, do not forget that the assembly will be appropriate for the required mechanical stress level. For this reason, systematically reviewing the elements that assure the panels against the potential environment stress of corrosion, and taking additional safety measures, such as the use of external straps to assure the paints to structure will be doing. By conclusion, the possibility of a hurricane posing a threat to PVS system installed in Cuba is low. Probabilistically speaking, the high expected annual loss concentrate primarily in panels and from the passage of a Category 4 hurricane, considering its high probability of occurrence and the destructive effect of its winds, are compared to the annual depreciation of the components. This is not exclude the possibility that the PVS will be affected by the more intense hurricanes, causing component losses beyond the probabilistic analysis obtained in the various studies. Several local storms, such as tornadoes, can cause significant damage to PVS system, but the local nature of their formation and development reduce the likelihood of them coinciding with the area where the PVS is located. This is all that we want present in this paper. We are in attention for you, please.
Have time for some questions. Anybody? This is to ask. From online also you can write or you can show your hand. You can ask directly. Okay, we have one question.
I have a question. We're aware that a tropical storm is coming towards Cuba right now. So I'm wondering if there will be a pre-calculated damage to the solar park installations or something like that?
No, in this moment we don't have any experience directly in the last year, because in the period 2024 and 2025 we don't have any hurricanes strong winds. Before 2024, we had only a few solar PV parks, and for last year and this year we increased the quantity of the solar PV parks in this moment, but we don't have hurricanes, strong winds, because for this reason we don't have any experience in this moment. But for this reason it's necessary to know how is the performance of another solar PV fields of solar PV system in another country in the region of the Caribbean region.
Okay, thank you so much for your time.
Anybody?
Thank you for.
No. Okay, I have one more questions. You have
Please.
demonstrated that PEG system, right? To improve the damages by like hurricanes. You introduce the PEG system of the PV systems, right?
Yeah.
So how like you consider it is like means better than other systems? Means it is not like you cannot find any complex, or it is not costly?
No, the problem is the possibility to obtain another technology to introduce in Cuba. No, For example, we can introduce the technology of the wind technologies so many years ago, but the fabric and the enterprise that produce this technology only can buy with different with a big park, park more than 100 megawatts, and it's not possible for us to use this technology in this moment. However, the solar technologies is very good for Cuba because the intensity of the radiation in Cuba is very similar in all the country, and for this reason, the government state decide to increase the number of the solar PV system in Cuba in first time, and in the second step is possible to introduce another technologies. We don't have rivers, we don't have so much biomass, and for this reason the problem is how to obtain a stronger electric power system with a high penetration of the solar energy. In this moment, we are working in this direction because it's like I said in the first slide, we need to use fossil oil because it's necessary to maintain stable the electric system. This is our problem in this moment because we have problem with the obtained fossil fuel. We obtained different technology in this moment. Don't forget that the technologies that we use in Cuba don't have more than 10% of the North American technologies. It's the law in the United States don't permit that technology with more than 10% of the American technology was included in Cuba.
Okay. So anybody? So I think we don't have any questions. So I really appreciate your work and your time. Thank you very much, Dr. Miguel Castro, for your presentation. So with this, we completed today. So just for reminding, tomorrow we start, I think 9:30 solid-state materials, and 12 p.m. we're having the second nano session. So please, so I humbly requested you to come that session. So with this, I announce the end of this session. Thank you very much.